All right, very good. Well, thank you everybody for spending another fun evening with us here. We've had a number of exercises with Aries and we're going to have some more, where we go simplex without using a repeater. And we occasionally are going to have that kind of need with ACS as well. In general, just to enjoy amateur radio, the more capable your station is, the more fun you're going to have, frankly. And certainly when the time comes for you to provide some communication link, whatever it may be, if you have a station that's working well and can reliably reach reasonable distances, then you're certainly going to have more to contribute to whatever that effort happens to be. So with that, let me do a share screen. We are building a capable station. The first rule is that any station is as good as the antenna system it has. You can have the best radio in the world. Connected to a junk antenna, it will perform pretty much like junk. If you have a modest radio, but a really good antenna system, you will get remarkably good results. So that's why we're really starting with antennas before we start with radios. The antenna is your link to the outside radio world. It collects the signals that are floating around out there, and it puts the signal out where you want it. And you, by choice of antenna, have some control over where it hears and what it picks up and where it sends. Unlike putting in an amplifier to make your transmit louder, an antenna improves both the transmitting and receiving. I know I've had plenty of opportunity to listen on different antennas on a given band from a given location around the world. And sometimes a change in antenna can make a remarkable difference in receiving. Now, by the way, on HF, we sometimes have separate antennas just for receiving. They tend to be very directional. Some are called beverages. They actually have relative immunity to noise, and they can be very directional, such as a long 3,000-foot wire headed toward Europe, for example. You can hear things on the low bands that you couldn't hear on your transmit antenna, no matter how good it is. For this particular presentation, we're going to be focusing on VHF and UHF, which means you're using the same antenna for both transmitting and receiving. The antenna that comes with the handheld is very inefficient. When you think about a quarter wavelength on 2 meters, which is about 19-20 inches, most of you do not have handheld antennas that are 19 or 20 inches, which means they have to do a compromise. And usually that means wrapping a coil around some piece of inert material and then covering it with some rubberized plastic. It loads from your radio okay, but it doesn't necessarily radiate very well. And the thing we're most concerned about is how well does it radiate a signal. There are aftermarket replacements. I know Dan and I use some aftermarket replacements. I've seen others who do the same. And they're usually a little taller, they're a little more efficient, they're marginally better, but it's really not the answer to having an effective station. So the real answer is you want an antenna that is separate from your radio and is put in a good location. Now, you can build a whole variety of antennas very cheaply. Some of these, actually, there are a couple that you could probably do under $1. You're looking at first a ground plane vertical, which is something that many of you may be familiar with, and we'll show you some pictures of things that you could build for under $5. A cubical quad, which you could probably also build for under $5 or $10. A well-known VHF ham, WA5VJB down in Texas, published articles on making what he calls cheap Yagis. And these are used actually for competition purposes by guys who, like me, who go roving around the different grid squares and countries and in contests. And it's less than $20 to build those. You can make copper pipe J-poles. Used to be able to build them for under 25. I don't know if you still can, because copper is more expensive at the hardware store than it used to be. There are actually some pretty good sources of scrap copper that will do just fine. All of these will handle plenty of power. A handheld antenna will handle maybe 5 or 10 watts. Some other commercial antennas have a limit of 200 watts, which is more than enough for most of you. But some of these antennas could actually handle hundreds and hundreds of watts with no problem. You can also buy them. You can get a mobile whip starting around $50 or less. You can get base verticals under $100 or up. You can get commercially made Yagis or beams, and we'll show you pictures of all these so you know what we're talking about. You can find good used antennas and clean them up and use them. I've seen so many antennas going for a song because somebody has to move out or clean up, or it's an estate sale or something. You can get some really good antennas and they're inexpensive. So let's start with a simple ground plane vertical. Now, these are all homemade, as you can tell, and each of them starts with basically a chassis connector. This happens to be a UHF chassis connector, the designation SO239. This is what you'll see on the back of most of the VHF, UHF transceivers that you buy, and HF as well. But the connector itself is available separately. They're inexpensive, and you see a variety of ways that people have turned them into antennas. The little prong in the center is what connects to the center of a piece of coax that you plug into it. And in this case, instead of it going to some place on a chassis inside a radio, it goes to a radiating element. That radiating element can be copper, number 14 or number 12 solid house wire, as shown here. It could be brass. It's about 1/10 of an inch opening there, so 3/32 inch brass rod would be pretty durable. It would probably stay up a little more stiffly. And then you attach radials to it, which can be soldered, bolted, any number of attachment means. It's a little hard to solder onto the flange here. Some of these SO239s, because it's not really an easily solderable material, and it takes a lot of heat. It's probably a lot easier to bolt them on. Now, there are connectors you can get that are silver plated. Those you can solder to much more easily. Attaching with some bolts and wire, it's an easy thing to do. The only skill you need here, really, besides being able to use a measuring tape, is to be able to solder. I don't know how many of you have soldering equipment at home. You probably have one of your fellow ACS members nearby who does have soldering equipment. If you don't, I think everybody ought to have at least a basic iron and a little solder and know how to use it. So here are some more simple ground planes that people have made. The one on the right here is made of those telescoping whips that you can get to replace those that are broken off so often in consumer equipment. And a little piece of aluminum that's been bent off at an angle, you can stretch these out, perhaps collapse. This may work on 70 centimeters. You stretch it halfway out and it works on 220. You stretch it all the way out and it works on 2 meters. It's all just a matter of the length of the elements. And then the way this one is configured, you can actually set it on a grass or something else. So you can see a variety of techniques there. Now here are commercial verticals. Now these are all omnidirectional we're talking about. That means looking top down around the compass, they radiate essentially the same in all directions. On the left, we have a typical commercial ground plane such as you may find from Comet or Diamond or one of those providers. You've got an NMO mount here in the middle. That's often used for mobile operation. The NMO mount, the NMO stands for New Motorola. You can get mag mounts with an NMO base. You can get NMO mounts that you poke a hole in the roof of the car, as I have done, and you mount them there, which is really the best way to do it. You can make your own mount that goes up on maybe a PVC pole and put an NMO mount in there and then mount the NMO on top of that. And then on the right, you have a simple mag mount that is not NMO, but accomplishes essentially the same purpose. So this gives you all sorts of choices to get something up in the air. And every one of these, even these little things, you know, with a couple of copper wires, will work better than the antenna that came with your handheld. Now, you might want to consider adding some antenna gain. What is gain? Gain is essentially the favoring of some directions at the expense of others. You can't create power where it doesn't exist. You can't create signal where it doesn't exist. You can focus, just as though you take a mag light, little mini mag flashlight, you unscrew the top and it becomes like a little candle. It's radiating that light in almost all directions. But you put that head back on, and now it's got a reflector that's focusing that same amount of light in a much narrower beam in both horizontal and vertical planes, and therefore you're getting a lot more light to that one spot where you're trying to get it. So gain really means less of your signal being transmitted is wasted in undesired directions. What's an undesired direction? Straight up is an undesired direction. Fortunately, most verticals have nulls going straight up and straight down. Let's suppose that you live down at the harbor and you don't really need to talk to somebody behind you because that's open ocean. Almost everybody you want to talk to is in an arc of maybe 90 degrees or 120 degrees to the north and northwest. There is also vertical gain, and this I want to show you. The little ground plane verticals that we looked at a few minutes ago will have a pattern on the lower, something like this on the lower left, and you'll see that a lot of the power is up through about 50 degrees or so, then it goes all the way down to the horizon and beyond. And you see that null I was talking about in the middle. If you could get gain in the vertical plate, like still omnidirectional now, you can kind of flatten this thing out and get something that looks more like what you have here on the right. You still have that null. Look where the bulk of your signal is. It's all in the first maybe 15 degrees. That's basically the horizon, and that's where the people you want to talk to are. Remember, unlike HF, the ionosphere is not going to refract the signal that goes up in some high angle direction and come back down somewhere else. It hits the ionosphere and just keeps going. The more signal you can put down toward the horizon, the more useful signal you're going to have. And you'll be receiving stronger from that same horizon area. Generally speaking, the longer the antenna, which means the more sections it has, the more gain it has. The more signal goes toward the horizon. Here are 4 examples I pulled from a catalog. This happens to be Comet. The first antenna is the GP1, and then you have the GP3, and then you have the GP6, which you see as 2 sections. There's a join right there. And you have the GP9, which is 3 sections, and you see 2 joints there. The joints are there because they want to make it easy to ship and store somewhere before they get it to you. The taller the antenna, the flatter that pancake, the flatter that pattern. It more looks like this. Having an antenna that's tall doesn't necessarily change the direction of what you're hearing, but it's certainly going to focus both transmit and receive signals at the horizon much better than the little short one will. Now, I mentioned situations in which you don't necessarily want to radiate in all compass directions. Directional antennas have gain both in elevation, which is this graph on the left, and in azimuth, which is the graph on the right. This is looking top down, if you will. And you can see over a swath of about maybe 70 or 80 degrees, that's where the bulk of the signal is coming from on receive and where the bulk of the signal is going to on transmit. There's a little bit off the back, but it's way down. These are calibrated circles, but you don't need to worry about the numbers right now. It just means there's some, but a lot less signal back, and off the sides, there are some pretty deep nulls. So what do those look like? Well, here's one. It's a homemade quad. Notice why do they call it a quad? It's basically a square of wire held out by some insulating rods. It could be fiberglass, it could be wood dowels. You got PVC here. One of these elements has the coax attached to it. The others have nothing attached to them. They're just there to help direct the signal in the desired direction. This one on the left is a little longer than the others. It's called a reflector. These 2 on the right are a little shorter than these, and they're called directors. You could have no directors, 1, 2, 3, 5, 10, whatever. And in each case, they'll start to get a little smaller and smaller as you go out. Now, the design can be a little complicated in terms of figuring out the dimensions, but usually when you find one of these things, somebody's already worked it out, published the results, and you'll get pretty good results from that. And you can see it's not going to cost a lot to build this thing. I mentioned WA5VJB. Here's a combination of 2 of his Yagis, one for 70 centimeter, those are the short elements, and a 2 element for 2 meters. And I expect this is being used, given the way it's being pointed, for satellite work. Some of you may have seen the Arrow antenna, where it uses basically Arrow aluminum tubing, and instead of a knock on the end, it has threading that thread into a boom. And its purpose also is to provide something you can point by hand at a satellite that's passing overhead. You don't have to use these for satellites. You can leave them at your house. If you're down in one corner of our coverage area, you can point it toward those other ends. Here's the URL. We'll make sure that's out available for people who want to build these things. This article has plans for antennas on 2 meters, 220, 440, 900, 1200. They're all cheap. It's house wire and small bits of lumber. Here's a commercially made Yagi. There are quite a few of these too. Cushcraft and some of the others have made these for years and years and years. I've got a couple of old ones. My old 4-element 2-meter is one that I used when we were doing our Battalion 5 exercise last year. I happened to be stationed with Julio up in the Universal City area. We were at the far north end of the exercise area. So rather than put up a vertical, I put up a 4-element Yagi pointed down toward the battalion headquarters, knowing that it would have pretty good coverage over all that area. Now, I also had to talk to Dan, who was up at North Valley Station at the time, but that wasn't a big problem because A, we're pretty close, it's line of sight, and there's enough signal coming off the back that it worked fine. But I wanted to make sure that we had a little extra signal going out to those areas where folks may have had less robust antennas. Maybe they were working out of their car. And so in this case, a small directional antenna like this worked just fine. Whatever you do in the way of antenna, you want it to be outdoors if you can. Now, I know some people who've worked successfully from inside office buildings that are highly elevated, and they stick the antenna facing out the window, and they have some really good coverage. I have a friend, no names, who actually tried using a UHF, actually a 1.2 gig radio, from the window seat of a flying aircraft, and it worked great. Other than that, getting it up outside is probably better. You have fewer obstacles, less chance of being absorbed by any metal that might be in the building. So you have a roof, which is a pretty obvious choice. You have patio covers. You have masts that sit on the ground, but you can attach to the fascia boards of your house and have it stick up above the roof so that you have some clearance. And the nice thing is, these VHF and UHF antennas aren't very big. They don't represent much of a wind load. So you don't need a tower. You don't need a real heavy-duty structure. A push-up mast, something with fiberglass, aluminum, whatever it may be, fine. If you have a metal support tubing, you're going to have to make sure that the radiating part of the antenna does not look into that tubing. Vertical antennas, vertical Yagis, for example, tend to be oriented vertically. The elements are going up and down. Well, if you're holding it at the mast, that first section of mast should probably be non-conductive, maybe a PVC or fiberglass, so that it doesn't interfere with that pattern, because now it's right in the way of the radiating of the driven element. You can use metal for the first however many feet and a short 3 to 5 foot insulating section for the very top, and then mount your antenna on that. And these things are light enough you can put them up without having to have a whole crew there to lift and help. If you have antenna restrictions, such as from deed restrictions in a homeowners association, there are some stealth antennas that you can use. One is called a ventenna. It's made to look like a standard roof vent, but it's resonant on 2 meters, I believe. You can put up an antenna and paint it to match the roof so that it's kind of camouflaged. If you make one of wire, it's so small that it probably will get lost in the roofing, and you just make it a dark color and nobody's going to see it anyway. Now, let's turn our attention to getting the signal from the antenna to your radio. So we're talking about transmission lines. Coaxial cable is a transmission line. There are other kinds. This is what we use most commonly. There are a variety of qualities and characteristics of cable. The better quality cable will generally have less loss than a shoddy imposter cable. If you use the proper connectors and install them correctly, you're less likely to have intermittent connections or other problems getting the signal from the antenna to the radio. All cable has loss. All coax has loss. In our being a better repeater operator, I likened the coax to panes of glass that you stack together to reach the distance you want. And there's some loss of light in each pane of glass. And if it's a smudgy, dirty piece of glass, you're going to lose most of your light very quickly. Even if it's good, if you have a whole lot of glass, you're going to eventually keep blocking the light in both directions. So just like that, coax, all coax has loss. The better it is, the less loss it has. It doesn't do you any good if somebody gave you a 150-foot roll of really good coax and you need 30, you got 5 times as much coax as you need, and therefore you're going to end up losing a bunch anyway. So try to keep the run not a whole bunch longer than needed. Leave a little extra for moving the radio around and being able to service the antenna if necessary. You know, you don't want to make it taut or tight. You want some flexibility there. Plan your run first, and then you'll know how much you're looking for. Now let's talk about cables. On 2 meters, here are some typical cables that people will use. And let's take a length of 50 feet. The results will differ, obviously, if you use a different length. 50 feet of RG58U, that's the stuff that's about 0.2 inches in outside diameter. And you'll lose about 56% of your signal. If you go up to RG8X, that's maybe a 1/4 inch or a little more in diameter, you'll lose 38% of your signal. Now that's transmitted signal and received signal. If you use LMR 240 UF, the ultra flexible stuff, I know Bill has helped people make some jumpers of this for connections around their station, but if you use 50 feet of that, you'll lose about 1/3 of your signals transmitted and received. Now let's look at RG213, formerly RG8. That's the standard black jacket, single coax braid, then polyethylene dielectric, and a copper center conductor. It's about 4/10 of an inch, almost 1/2 an inch outside diameter. You'll lose 24% of your signal over 50 feet. If you go to LMR 400, the Times wire, it's not semi-rigid, but it's kind of stiff compared to these other cables. Most of them have a stranded center core, which makes it a little more flexible. The LMR is a little less flexible. You can get it through a swept vent pipe and things like that. You can bend it around. You'll lose 16% of your signal. Pretty good. If you use something like Andrew or Comscope LDF 450, this is a traditionally called heliax, but it's actually not helical anymore. It's semi-rigid line. Even though they don't make it helically wound anymore, you'll still hear it referred to as heliax. And there are various different sizes of that. Some of them are about as thick as my arm. Some of them are about the size, smaller than the size of my little finger. Generally, this kind of cable, or any cable with the same construction, gets larger, the loss goes down, and the power handling capability goes up. It becomes a little more expensive. The connectors may be a little more expensive, and it becomes a little harder to install. All of these are very practical in terms of installing them, bending them around if you need to move them around a joist, if you snake them through the attic section of your house. They're all quite workable. Now, remember, technicians, everybody, including technicians, has access to 6 meters, and techs have a portion of 10 meters. The 10-meter portion you have access to is 28.3 to 28.5 megahertz. That's single sideband only. Some radios, such as the quad banders like the FT8900, they include 10 meters. That 10 meters is FM, and a technician cannot use FM on 10 meters. So make sure that just because it's there on your radio, don't think that you can use that. You will need a general class or higher to use 10-meter FM. But on 6 meters, you can use whatever mode is allowed there. A 6-meter dipole is only 10 feet long. Not hard to fit something there. It's 2 legs of 5 feet each, one connected to the shield of your coax and the other connected to the center of your coax. The 10-meter dipole is a little longer, 17 feet. Each leg is about 8.5 feet. These are strung horizontally. If you're working 6-meter FM, you could actually build a 6-meter dipole, hang it from one end, have it go vertically, which a lot of people are using when they're on FM. They're using vertical polarization. And again, it's just wire and coax. Here are some simple dipoles. You could make a dipole for 2 meters, as a matter of fact. Doesn't have to be a ground plane. But remember, what we're showing here happened to be in the horizontal direction. There is significant loss between a vertically polarized antenna and a horizontally polarized antenna. It can be significant. You'll notice also there are insulators on the end. The insulators are not just there for decoration. When you're starting to use serious power, several hundred watts, on any dipole where these are 1/4 wavelength long legs, there's a high voltage point at the end. But you don't want that arcing to a local tree or to something else. So the insulators are there to prevent that arcing. The power levels you're using with mobile radios, that's really not an issue. You could, for example, build something like this for 10 meters, even 2 meters. You could hang it from one end, from a tree or what have you. Now, the thing you don't want to do is have the coax droop down to where it's parallel with the other element. It kind of has to stay out of the way of the antenna's pattern for a few feet before you bring it in. You can see they've used PVC hubs, they've used injected plastic. Here's a piece of simple plate, plastic plate sheet that has been drilled to hold the connector and to hold the ends of the wire. Anytime you're building a wire antenna, the wind is going to whip that wire around a little bit. So you kind of have to be careful about making it too stiff. I tend not to want to solder things like that because solder stiffens a piece of wire. And as it flexes and flexes, eventually you'll get a break there. Better to crimp and bolt and let the flexible wire do its thing in the wind, and that will reduce the chance that it will break. But here's that same connector that we used for the ground plane verticals. Same connector that's on the back of your radio pretty much. Whenever you are installing an antenna, we want to make sure that you're safe. Many of us are okay with climbing. Some of us are not okay with climbing. Some of us absolutely should not climb. If you want to put something on a roof or in a tree and you're one of those people that is not both equipped and comfortable and competent in climbing, you can hire somebody to put these things up. It's not a big deal. If you tell them what you want done. Commercial tree services, they got guys who will climb up any tree. I've handed them up a battery powered drill and a screw eye, and I have them drill a small hole into the tree, and it usually doesn't hurt the tree. And then I have them tie in a pulley and a big loop of non-conductive cord like Dacron, polyester covered Dacron cord. And then I can attach and pull up any antenna I want there later on. And if they're doing work on the tree anyway, doing that extra is really nothing. There are roofing contractors. They spend all day up on roofs. If you need them to go up and clamp a mast to a vent pipe or hook something up to your chimney, they can do that easily. If you're not comfortable being up there, get somebody else to do it and hire somebody to do it, and you should be good. The other thing you have to be careful of is staying clear of electrical wires. Magazines occasionally show stories of somebody who was putting up a tower or a mast or changing out antennas, and something came in contact with a line wire, electrical wire, 120 or higher voltage, and somebody was killed. You absolutely don't want to do that. Always look around at where the wires are and make sure that there is no possible way, even if the wind blows, even if something falls off, that it could contact those wires. That's a clear safety thing. Speaking of that, this is not directly related because it's probably more than most of you are ever going to do. A good friend of mine did some analysis on accidents, deaths in ham radio caused from various lapses in climbing and so on. Sometimes it was a hardware failure. Sometimes it was a failure to use proper safety equipment in the right way. And he created a nonprofit group called Zero Falls Alliance. He's done some talks. One of those talks is on YouTube. It's about an hour. I would recommend to each of you that you spend an hour, listen to Jim's talk. His name is Jim Idelson, K1IR. And again, it's Zero Falls Alliance. And watch that video and understand better what some of the risks are in terms of hardware deterioration, improper safety equipment, improper use of safety equipment, various other causes of accidents, with the objective of getting everybody educated to the point where even if you're asked to help somebody else on an antenna project, you'll have a good idea what's safe and what's not safe. Invest an hour in that and remember the lessons, and I think you'll find it will be time well spent, and somewhere down the road, you may save yourself or somebody else from a serious accident or worse. That is the formal part of the talk. There may be some questions, and I'd be happy to take those. We will be covering radios and power sources. Once you have your antenna up, you've got to hook something to it. And so we'll be talking about that next time. So with that, let's see if we can unmute some folks and take some questions or comments.
Marty?
Yes.
You might want, for those that are newer at this, I know I had some confusion when I started. Explain the difference between vertical and horizontal polarization in terms of FM and the kind of antennas we're allowed to be using.
Okay, good point. I mentioned briefly that most people who are on FM are using vertically polarized antennas. Now, in the case of a ground plane vertical, the part that sticks up straight is vertical with respect to the ground, with respect to the horizon. The radio wave it launches is oriented up and down. And it will be best intercepted by another antenna that is up and down. If the antenna is crosswise, I mentioned you have loss. One signal's coming like this, one's looking like this. There's going to be very little intersection there, okay? So you're better off trying to match that polarization. Now that's true until the signal bounces off something. In the case of HF, bounces off the ionosphere. In the case of VHF and UHF, it may bounce off a mountain or a building. Once it bounces, the polarization becomes what they call elliptical, which means you can't really predict what it's going to look like when it gets to your place. And so polarization becomes less of an issue. In fact, transmit hunters, the guys who go around looking for hidden transmitters, both for sport and for serious, one of the tricks they use is to use a Yagi horizontally polarized, and they'll turn it around. And if they find a peak of a signal, they think that might be the source. They'll take it and turn it so that instead of the elements going this way, now they're going this way. If the signal changes, they say, oh, I have a direct signal. If it doesn't change, they say, oh, it must be bouncing off something, so that's not the real direction I want to go. It's pretty clever. So those folks who are primarily into weak signal work, single sideband, CW, some digital like FT8, more often than not, they will use horizontally polarized antennas. And that means the elements, in the case of a Yagi or a dipole, are parallel to the ground. The only place where it's not obvious whether it's horizontal or vertical because it looks the same in both directions is something like a quad. And in the case of a quad, determining whether it's horizontal or vertical depends on where you put the feed point. You have this loop of wire. You got to break it somewhere and put it to the connector. If you put it on the bottom of the connector, it's actually horizontal. If you put it on the side of the loop, rather, then it's vertically polarized. But again, almost everybody we have in ACS is using vertical polarization. On our Aries nets each week, we have a post net that's either simplex or sideband. Once a month, it's single sideband. And we just use vertical polarization anyway because that's what everybody already has. So there's no magic that it has to be one or the other. The main thing is that you match what other people are using around you. And since in the case of mobile operation, it's almost always vertical just because of the way it's mounted. Mounting verticals on roofs is fairly easy. You would only need one attachment point. So verticals are the common antenna for pretty much all FM communication and for an awful lot of even sideband work. But the serious guys have horizontal polarization. So just mainly think about where the radiating element is pointed. If it's up and down, it's a vertical.
Martin had a question. He wanted you to discuss open wire or window line or.
Okay, good. We had a little discussion of that. AJ raised that at our last session. Open wire line is basically two parallel wires. Coax is with one wire shielding another one. So the RF, the radio energy, goes between the inside of the shield and the outside of the center conductor. In the case of twin lead or ladder line, you have two wires running parallel, usually kept that way by some spacers every so often, or by plastic with windows cut in it. And those have a higher impedance, typically anywhere from 300 to 600 ohms or more. And they're very, very low loss, even at VHF. The problem is anytime you get them near metal, like a gutter or a windowsill, it really screws up their pattern. So you almost have to have special feed throughs to make sure that you don't disrupt that. The other problem is a mechanical one. You're using these long wires that have connector, you know, especially the window line, it's got some surface area to it, and it can twist in the wind. And as it twists, you start work hardening the wire, and eventually it can break. There are tricks to that too. You put one complete turn of your twin lead about every 10 spacers, and you can have it kind of twisted. That helps cut down on the wind movement. But still, they're more physically fragile. A piece of coax you can lay up against a gutter, it's no problem because the signal's all inside it. You can coil it up, no problem. You can't coil up a piece of twin lead. So there are people who've used twin lead for VHF. One guy up in Canada used twin lead for his moon bounce array. This is where you have a huge number of antennas with lots and lots of gain pointed at the moon, and enough gain that they can hear that weak signal bouncing off the moon from somebody else. It's a huge.
I use it very successfully here on HF.
On HF, it's much more popular, and especially if you're using a non-resonant antenna. Some of these off-center fed and Wyndhams and so on, they don't have a 50 ohm impedance, so you don't have to worry about trying to match a dipole. You just run it down, and then you'll have to have some sort of tuner at the bottom end to convert it to the 50 ohms that your radio is looking for. Bill, what do you use to do that?
It's about 72 feet long total, center fed into a Heathkit tuner. Sometimes I go direct into the tuner, which forces it into a 4-to-1 balun, or I have a 1-to-1 outside with some extremely low loss coax to bring it inside, very short and very low loss, into a Heathkit again.
Into a tuner, yeah. By the way, an antenna tuner is basically a collection of some inductors and capacitors. It's two components, and usually you make them adjustable so that you can bring the match down. They will transform the impedance from whatever's at the radio end of the line to whatever the radio really wants to see. It takes some adjusting to do, but tuners, there's some very robust tuners out there, but most of them are built for HF. They're not built for VHF and UHF. During my days as ARL Vice Director, I used to visit a lot of field day sites, and one of the sites that was really fun to visit was a group called the Zuni Loop Expeditionary Force. And it was a bunch of guys who worked low power CW, just Morse code, for field day up in the San Bernardino Mountains. And they put up some very elaborate wire Yagis in the trees. I mean, they'd shoot them up and then have another element over here, another element over here. And they were very loud, which helped make up for the fact that they were running very low power. And then they had these little mini tuners. And because they're only running 5 watts, these tuners didn't have to have a lot of power handling capability. So they built these little mini tuners to tune into their radios, and they did extremely well. But again, HF, it's popular because the losses generally, even in the transition, are lower, and it's not hard to put up an antenna that's resonant on 2 meters or 70 centimeters. It can be harder to put up an antenna that's resonant on 80 or 160 meters just because of the sheer size, or run multiple bands off the same antenna. And this is where sometimes people will put these off-center fed and other kinds of non-resonant antennas up and then use the twin lead to bring it back down.
Because we live in the city, what is the relationship to antennas and man-made noise?
The relationship is antennas will pick up noise just like they pick up radio signals. The good news is for VHF and UHF, most of the noise that's generated tends to concentrate in the lower frequencies, certainly from motors and things like that, and then and switching power supplies, which are everywhere, and you'll find them showing up every 60 kilohertz or something in your HF bands. By the time you get up to 2 meters and so on, there's very little of that noise left. So fortunately, we don't have to deal with it often. When you have a situation, somebody has their speaker on. When you have a situation such as we did the other night on one of our nets, where you heard a kind of motor noise or something, I mean, it was actually somebody else probably operating very close to the input of ACS1, and they were loud enough that weaker stations had that noise superimposed on it. But that's a different kind of noise than the stuff that we typically get from TVs and computers and so on. That kind of noise is rampant on HF, and it's a constant source of hunting for the noise and trying to find ways to get rid of it, to ground things, to use ferrite cores to act as chokes to choke out the noise from a common mode signal that's on a line. Often just chasing down the RF noise that's in your own station can be a real challenge, let alone the stuff that's being generated outside. But on VHF and UHF, it's really much less of a problem. If you find there's some noise source, very likely it could be in your own station and getting into your radio directly or through the power line rather than through an antenna. If you do have a noise problem, there are some devices that will help find it and cancel it out. Usually what they'll do is they'll have two antennas. One is the antenna you're using to listen to the intended signal. The other one is called a sense antenna, and you'll place that somewhere near the noise source if you can find it, or in the direction of the noise source. And then the box you adjust so that it basically adds an out of phase signal from that noise antenna and cancels it out and allows you to hear much better. Those boxes actually work very well. Again, there isn't much of a need for that on VHF and UHF. On HF, that can be really helpful.
Well, I want to thank Marty, and I think it came out really great, and I will go ahead and check through the recording and see if we can be able to edit it down. It seems like that is a nice way to be able to kind of save it for posterity.
Hank, you did a spectacular job on the last one. I know it took a lot more time than you hoped it would, but thank you so much. I hope I gave you less to edit out this time.
Well, we'll find out. You know, it's just one of those things. But I want to thank everybody for coming by, and enjoy.
Okay, and thank you, Hank, and thanks everybody. Had fun.
Happy editing.
Thanks, Marty.